Have you ever just stopped and wondered how your phone, your email, your entire digital life seems to just magically sort itself out? How it seems to know exactly where everything belongs? Well, I'm going to let you in on a secret. It's not magic. It's machine learning. And today we're going to peek behind the curtain and meet the different sorting hats that make it all happen.
I mean, think about it. You open your inbox and it's already separated the important stuff from the junk. You fire up a movie app and it knows without a doubt that one film is a comedy and another is an action-packed thriller. This amazing trick has a name. It's a core concept in machine learning called classification, and we're about to break down exactly how it works.
So the whole secret sauce here is classification. Now, for a minute, I want you to forget about predicting exact numbers. Classification is all about putting things into distinct buckets or categories. Is this email spam or not spam? Is the student going to pass or fail? It's the art of making a choice between a set of options.
To really get a feel for this, let's put it side by side with its cousin in machine learning, regression. See, regression is all about predicting a continuous number, like the price of a house, which could be, pretty much any number. But classification, that's what we're talking about today, is totally different. It's about predicting a specific fixed category, pass or fail, yes or no. It's not about how much, it's all about which one. Okay, so how does machine actually learn to do this? Our first strategy is a very logical, very mathematical approach called logistic regression. Now, I know you're thinking, we just said we're not doing regression. Yeah, the name is a little confusing, but trust me, its goal is pure classification. It's all about finding the perfect mathematical dividing line that separates one group from another.
Let's call this the mathematician's approach. There's no guesswork here, no kinda sorta. It uses a precise formula to draw a clear boundary. If a new piece of data lands on one side of that line, it's category A. If it lands on the other, it's category B. It's clean, it's simple, and it's perfect for those clear-cut yes or no questions, like figuring out if a credit card transaction is fraudulent.
All right, let's put this mathematician to the test. Here we've got some data on a few students, how many hours they hit the books, and whether they passed or failed the exam. A 1 means they passed, a 0 means they failed. Simple enough. So here's the puzzle. A new student comes along who studied for exactly 5 hours. What's the prediction? Pass or fail?
This is where the math kicks in. The algorithm uses this really clever formula called the sigmoid function. Now, don't worry about memorizing the formula, you don't need to. All you need to know is it's one magic trick. It can take any number and squash it down into a probability, a value somewhere between 0 and 1. And that probability, that's the key to everything. So, we take our 5 hours of study time, we plug it into that sigmoid function, the gears turn, and out pops this number, 0.818. Now, that's not just some random number. That is the model's calculated probability that a student who studies for 5 hours is going to pass. To put it another way, there's an 81.8% chance of success. And here's the final crucial step. We set a decision threshold, usually right in the middle at 0.5. Since our result, 0.818, is way above that halfway mark, the model's prediction is crystal clear. It confidently classifies the result as a pass. It drew its line in the sand, and our student is safely on the winning side. But what if a problem isn't so black and white? What if you don't want a strict mathematical line? What if instead you'd rather just ask around for opinions? Well, that's the whole idea behind our second strategy, k-nearest neighbors, or kNN for short.
People often call kNN the hello world of classification because it's just so intuitive. Let's call this one the Pollster's approach. To figure out what a new thing is, you just look at its closest neighbors and see what they are. It's a vote. This is super useful for things like recommendation engines, suggesting a product based on what other similar people have liked.
Okay, let's put our Pollster to work. We've got a small data set of movies here. For each one, we know its IMDb rating, its runtime, and its genre, either action or comedy. This is our training data. Think of this as our little community of neighbors who are ready to vote. And here comes the newcomer. The movie Barbie arrives on the scene. We know its rating and we know how long it is, but we have no idea what its genre is. So the question for our kNN Pollster is, based on the neighbors we already know, do we classify this as an action movie or a comedy? So the first thing we have to do is figure out who the neighbors actually are. The algorithm does this by calculating the distance between Barbie and every other movie, based on its rating and duration. You can see the numbers here. It's pretty simple. The smaller the number, the shorter the distance, and the closer the neighbor.
Okay, it's time to take the vote. For this, we'll set our K to 3, which just means we're going to ask the 3 closest neighbors for their opinion. Looking at our distances, the 3 closest movies are OMG 2, Mission Impossible, and Rocky or Ronnie. And as you can see from this vote tally, that gives us 2 votes for comedy and 1 vote for action. And the final step is the easiest one of all, the majority rules. With 2 votes against 1, the kNN algorithm confidently classifies Barbie as a comedy. See? No complex formulas, no hard dividing lines, just the simple wisdom of the crowd. All right, our final strategy takes a completely different approach. This isn't about drawing lines or asking neighbors. This is all about playing the odds and looking at the evidence. Let's meet our third and final algorithm, naive Bayes. Let's call this one the detective's approach. So imagine this. You find a red ball. The question isn't, what's the chance of picking a red ball? No, the detective asks, given that this ball in my hand is red, what's the probability it came from bag A versus bag B? It works backwards from the evidence to find the most probable cause. This approach is an absolute powerhouse for things like text classification, like figuring out if an email is spam based on the words inside it. Okay, let's give our detective a case. Here's some medical data on a few patients. We've got notes on whether they had COVID, the flu, and a fever. These are our clues, our pieces of evidence that we're going to use to make a prediction. Now, a new patient walks in. The evidence is clear. They've tested positive for both COVID and the flu. So our detective, the naive Bayes algorithm, has to figure out the most likely outcome. Based on all our past cases, is it more probable that this patient has a fever or that they don't? So the algorithm gets to work. It calculates 2 competing probabilities. First, what's the probability of fever, yes, given our evidence? And second, what's the probability of fever, no, given that same evidence? The results are in. As the chart shows, the chance of having a fever is about 0.17, while the chance of not having one is 0.13. Since 0.17 is higher, the detective's conclusion is clear. We predict a fever. So there you have it. 3 totally different ways of thinking, 3 completely different logics, but all of them are aimed at solving the exact same problem. How do we put a new piece of data into the right box? Let's do a quick recap of what we've covered. So let's put our 3 sorting hats side by side. First, we had the Mathematician, Logistic Regression, which uses a strict formula to draw a dividing line. Then we had the Pollster, k-nearest neighbors, which just takes a democratic vote from the nearest data points. And finally, we had the detective, naive Bayes, which uses probability to work backward from the evidence to find the most likely culprit. Each one of these sorting hats is working behind the scenes in the technology you use every single day. So next time your inbox is perfectly organized or you get a movie recommendation that's just spot on, you'll know the kind of thinking that made it happen. So the question I'll leave you with is this. Now that you know how they think, which of these strategies do you see working in your world? Are your apps run by the precise mathematician, the democratic pollster, or the evidence-based detective? Something to think about.